Good morning, champs. Today we're diving into line integrals, the idea of measuring something along a path. It's like regular integration, but instead of a boring straight line, we follow a curve, sometimes even in 3D. Let's see how this works. First, what is a line integral? Imagine you're walking along a path, and at each point there's a force field, like wind or maybe gravity. A line integral tells us the total accumulated effect of that field along the path. In formula terms, if your curve is given by x of t and y of t, then the integral is the dot product of the field with the tangent vector, integrated over t. Don't worry if that sounds abstract. Let's see some concrete examples. Example 1, the circle. Take a look at this graph. You see the vector field spinning around the origin and the red circle path going counterclockwise with the start point marked. Now, let's compute the line integral of the field f of x and y equals minus y, comma x along that unit circle. The parametrization of the circle is cosine t and sine at. Its derivative, the tangent vector, is negative sine at and cosine at. When we plug this into the field, we get the same vector, negative sine t and cosine t. Taking the dot product gives sine squared plus cosine squared, which is always 1. So the integral is just 1 integrated from 0 to 2 pi. That adds up to 2 pi. Nice and clean. Now look at this 3D graph. The gray arrows show the vector field, and the red helix spirals upward through it, like a spring. The field is f of x, y, z equals y, negative x, z. And our path is chosen to trace that helix, cosine t, sin t, and t divided by 2 pi for t between 0 and 2 pi. Why this parametrization? Because the cosine and sine keep us circling in the xy plane, while the t over 2 pi in the z direction makes us climb steadily, 1 unit of height for every full turn. The tangent vector comes out as negative sine t, cosine t, and 1 over 2 pi. The field along the path is sine t, negative cosine t, and t over 2 pi. Take their dot product. That's negative 1 plus t divided by 4 pi squared. Now integrate from 0 to 2 pi. The result is negative 2 pi plus 1 half. So the answer is minus 2 pi plus 0.5. That negative result means the field resists the motion along the helix more than it helps. And that's the magic of line integrals. Whether you're looping around a circle or climbing up a helix, the recipe is the same. Parametrize the curve, take the dot product with the field, and integrate.